Hey there, calculus fans. I'm Dr. Andy Lovelace, an instructor at the University of Washington. Here I'm going to give a proof of the derivative of the log of x. Now, in order to give this proof, we do have to know a little bit about the symbol e. And I have that in a separate video, so check that out because I talk about the history, but really the main fact I need is this fact. And that's part of a much larger story of why that comes out, anyways, check that out. But mostly I just want to use this as an opportunity to go and talk about this. So given a function, right now we're going to use the natural log. And just briefly, if you don't know how that's defined, if you have y equals e to the x and you want to get x by itself, we need to give that a name. And the name we give it is the natural logarithm. So we write the natural log of y equals x. Those two things are the same. And that bothers some students in some way, but in my view, inverses, yeah, that has a weirder name, but when I say that y is equal to 3x and y over 3 is equal to x, that usually doesn't bother students, because they're used to the words multiplication and division and the symbols that go with them. But it's the exact same idea of inverse. Okay, so let's just say we've defined this unusual thing that we call the natural logarithm, and it cancels off the e to the x in this way. Okay, so now a reminder about the definition of the derivative. The derivative tries to say I have some graph. Why don't I actually draw an accurate graph? It says I have a graph and I would like to define slope. But I can't define slope at one point. I need two. So we pick a point nearby. So here's x plus h. This is f of x. This is f of x plus h. And we compute the slope between those 2 points. And we try to find a pattern. If we can find that pattern, x plus h minus x is just h, then we can take the limit as h goes to 0, and that's the derivative. So that's true for everything. We're just going to apply it now to try to find the derivative of the log. So we need to simplify this to a place where we can plug in h equals 0 and make some sort of deduction. Okay. So what are we going to do? So to me, the natural thing is to try to use the rules we know about logarithms. And one of them is that the log of a minus the log of b. And that's a separate thing. It's always a question of how deep do we want to dig? And are you asleep yet in the video? So I got to watch how deep I dig here. But we can use that rule and write the limit as h goes to 0 of the log of x plus h over x over h. The log rules are really the exponent rules in reverse. If you wrote e to the a, e to the b equals e to the ab and then rewrote it with logs, you get a similar rule. If you had e to the a over e to the b, and you wrote this, that's actually where this rule comes from. But that's a different story for another day. Okay. So if we're trying to analyze this, is there anything else we can do? Well, we could write this as the limit as h goes to 0. And let's just see if we can think of any other ways to write this. Well, definitely I could write the log as x over x, which is 1, plus h over x. Okay, I don't quite see how that's helpful. But then I could take this h that's on the bottom and write 1 over h. And then we have probably the most important log rule of all is this one. This is the log rule you use every time you solve. So that's it. So then we can write the limit as h goes to 0. And it's always going to be, if you're doing a proof about logs, you're going to have to use a lot of log rules. Okay? All raised to the 1 over h power. So all we've done is a bunch of rearranging here. and we're hoping we're getting somewhere. All right. So the main question is this 1 over x. So let's see if we can go one step further. The limit. Well, one of two things we can do next. But let's say I wanted to make it look exactly like this. Is there any way I could do that? Well, the only way that would happen, so this is just a sort of a direct approach, is if 1 over n was in this spot. So let's say I could somehow get it in that spot. Well, I'll have to think about that a little bit. How could I do that? What would h have to be? So right now I'm hoping I can make it look like that. And unfortunately my h's look like n's. So I'll try to really pronounce the tail there. But x over n would have to be h. Okay. How does that help me? So let's just rewrite it. I'd have the limit. I'll worry in a moment about filling this in. I'll have 1 over n. Okay, that accomplished that. But now I'm going to mess up something else. I'm going to mess up the 1 over h. So what can we say about 1 over h? Well, 1 over h is going to be n over x. So let's write this as n over x. I still don't quite see how that's helpful. And also the h went away. But if h is going to 0, what can we say about n? Where would n have to go in order to make h go to 0 if x is fixed? Well, n would have to go to infinity. You can also see that here, if n is going to 0 from the right, this goes to infinity. So some subtle little pieces I probably should have talked about in more detail there. But anyways, at this point, we have it. We have the log, and I just have to put it in a lot of parentheses. I was trying to make it look exactly like our result. We have this, all raised to the 1 over x power, and all inside the log. This is not a very clean proof I'm giving, but we're getting it done. In class, I just give people kind of the general, but this is approaching e. Why would that be helpful? This is the limit as n goes to infinity of log of e to the 1 over x. And those two cancel. You get 1 over x. So I don't know if that was informative. The proof that I usually show my business students is this much shorter version where I rearrange like this. I guess I do that same proof. I didn't. I should have prepared and I saw this. So anyways, that's what we get. If you're curious about the derivative of other log functions, there are, and I should say, this visually makes sense. You always should check everything. Don't just blindly trust everything I'm doing. But if you get this function, it would be interesting to ask yourself, if you were standing here at 2, what do you think the slope would be? Well, it should be less than 1. And if you're standing here at 3, what do you think the slope should be? Well, it should be smaller than the slope was at 2. And if you're standing at 1, what do we think the slope might be? And then you could try out your formulas. This says this is the slope. And so this is predicting that the slope at 1 is going to be 1, or 1 over 1. The slope at 2 is going to be a half. The slope at 3 is going to be a third. And it is nice that way. Okay, if you had some other log, y equals the log, base a of x, there's a few ways you can go. I mean, this is the same. There's 2 steps. If you don't know this rule, you can write this as the natural log of x over the natural log of a. and those are the same. If you don't know that rule, I could derive it in a moment. You also can rewrite it as a to the y equals x and then differentiate with respect to x. But I'll talk about that in the next video when I do the exponential functions. So if you differentiate this with respect to x, you get y prime, this is a constant, 1 over the log of a, times 1 over x. So that gives us our full complement of our rules, which is that the derivative of the natural log of x turns out to be 1 over x, and the derivative of some other log, and I can hardly ever remember using this, is 1 over x times 1 over the log of a. So there you go. That's that rule. How we typically see this appearing in action is there's other stuff going on. So you still have to combine these with other rules. So if I say the log of x squared plus 3x to the 10th, you're still going to need all your other rules, right? The derivative of the 10 is 10. This is the chain rule question to the 9. Then you take the derivative of the inside. But first, you got to leave this alone. Times the derivative of the inside, which is 1 over x squared plus 3x. And then times the derivative of the inside of that, which is 2x plus 3. Now in these situations, we typically put it up here. So if you look in a textbook, they might mention things like, hey, if all it is the log of some mess, and you go to take the derivative, you could put whatever's on the inside on the bottom and put the derivative of the inside on top. But that's just a clever way to say the chain rule. All right, hope you found that interesting. Let me know if that was helpful.